We are continuing the creation of shear force diagram in this video, and in this particular video we are doing or creating a shear force diagram for a force system with a uniformly varying load. What is a uniformly varying load? You can show a uniformly varying load like this. You will have a uniformly varying load like this, where you have a maximum magnitude at one point, say for example 10 kilonewton here, and 0 here, which will be acting over a beam just like this. So you have supports at A and B, and a load will be like this. So you can calculate the force at the maximum force at any point if you know the length of this the length over which the force is acting. Now if it is like this, then the slope of this curve or the force distribution is, or the rate of change of the force is the slope of the curve, which can be calculated as C equal to maximum force over which the length is acting, that is 10 over 10. So 1 is the rate of change with distance. So from here it's 0, and at distance x from 0, say you consider a distance here, let's call this x. At x the maximum force will be 1x, because this is the rate of change and x is the distance. So at that point it will be 1x if this is x. Now this is how you calculate the load at different points. Now the total load of this force system will be the area of this triangle, right triangle, which is half b times h, which is half 10 times 10, which is 50, and that will be acting through the centroid of this triangle. Now the centroid of the triangle is 2 into this distance over 3 from point here, or 10 by 3 from this point. So if you have 2 points, say C and D, C and D here, then the centroid will be somewhere here, passing through this, where this distance will be 10 by 3, and this distance will be 20 by 3, or 2 times 10 by 3, and the effective force 50 kilonewton will be acting on this line. So you can draw that force here. So the total force of this force system will be acting through the centroid of this area. Now let's see if we can draw a shear force diagram for a force system like this. Let's consider the same cases as before. You have a 10 kilonewton force, a maximum force, and 0 here, acting over a length of 10 meter, and you have 5 meter here, 5 meter here. Now total load is of this force system is half times 10 times 10 equal to 50 kilonewton, and that will be acting at, let's say, A, B, C, D, and that will be 50 kilonewton will be acting at from C it will be 20 by 3, and from D it will be 10 by 3. So this will be acting at 10 over 3 from D, or 20 over 3 from C. So you can draw the equivalent diagram for this case, where you have your beam like this, and then you will have your force system, or the equivalent force of that force system, acting at a distance which you can calculate with this information. So this distance will be 10 by 3 plus 5, and this distance will be 5 plus 20 by 3, which will be 10 by 3 is 3.33, so that is 8.33, and the total distance is 20, so the other distance is 10 by 3 is plus 5 equal to 20 minus 11.67, and the magnitude of this load is 50 kilonewton, which we calculated here, the total load of that force system. And you will have your reactions at A and B. Now, using the equations for equilibrium, that is summation of forces in x direction equal to 0, summation of forces in y direction equal to 0, and summation of forces, moments about z equal to 0, this is cancelled because there is no force in x direction, and this will give you RA plus RB is equal to 50, and this will give you, taking moment about A, you have RB at 20 meter from A, so 20 RB is equal to 11.67 times 50, or you have RB is equal to 11.67 times 50 over 20, that is 29.18, and therefore RA will be 20.82. Applying this condition in here, we can calculate RA, that is 20.82. So you have RA and RB. Now you can use your original diagram to calculate. I'm just copying this diagram to the portion below, so it will be visible when I do the calculations. So I'm just copying that to here. So you can use this for further analysis. Now we have calculated the reactions at A and B, and also calculated the total load of the force system. Now you need to use the same old method that we used to calculate the shear force diagrams, that is assigning sections between each points where there is a force change. So between A and C, in this case, when you start taking sections, make sure you take the first section near to the point where the apex of the right triangle is. Don't take a section here near the base of the right or the maximum point of the right triangle. Take from here. So first section should be between A and C, and that applies whenever you do a problem involving uniformly varying loads. Always take the section starting from this side here, or depending on the direction of the force. If the force is 0 at this end, then take the section from here. I will explain it why that is required, or you will understand it why that is required later on. So taking a section between A and C, you have RA here, and a section like this, X, this is X. So X, maximum distance of X is 5, X is 0 here and 5 here. So at X equal to 0, force is RA, and at X equal to C, which is 5 meter, at X equal to 5, force is RA again. There is no force, it is 0, so it's still the reaction at A. Now you take the section between C and D. So that goes between C and D, you have RA, and your load going like this. This is 5 and this is X. So we calculated the intensity of this this force as 1. How do we calculate the intensity of that as 1? Because it's span over a 10 meter length, and the maximum load is 10 kilonewton. So the slope of this line is 10 over 10, or the intensity of force is 10 over 10, that is 1 per meter. For every meter you will have 1 kilonewton increasing. So at x, for x distance, the increase in force will be 1x. So you can calculate the intensity of force at this point, which is at x distance from here. So the intensity of the maximum intensity of force here is 1x. And therefore the area of this triangle can be calculated. The total load in this case for this hatched area, total load of uniformly varying load is 1x over a distance of x. So half x times 1x, half x times x, that is x squared by 2, x squared over 2. That is the total load, and that will be well, you don't really need that where that load is acting. So you can see this the load is actually varying following a square law. So at this point the total load is x squared by 2, x squared over 2. So at x equal to 0, the force is Ra plus x squared by 2, which is 0. So Ra plus 0, that is equal to Ra. Now the maximum distance of x is 0 to 10. So 10 is the maximum distance of x, and therefore you have at x equal to 10, force equal to Ra plus 10 squared by 2, that is Ra plus 50. Now you can see 50 is the total load of this force system as we calculated here. So at this point here you will have the total load will be acting and plus the reaction at A. But because the force varies based on square law, you know whenever there is a variation based on a square law, that cannot be drawn as a straight line. It will be a curve. We will come to that later on. Now you take your section between D and B. So between D and B, what you have is your so this is your section here, and let's take this distance x, and this as 10 and this as 5. So there is no changes between these two forces, so these two places. So at x equal to 0, which is this point, force is this one, which is Ra plus 50, and at x equal to 5, force will be the same because there is no variation. Now you can draw your shear force diagram. How do you draw that? Let's draw the shear force diagram from here. So how do you draw the shear force diagram? Let's complete it using a baseline which is shown as your beam here. And let's consider each sections one by one. The first section was this one, and the forces are Ra on both these sections are 1 and 2. So between A and C the force remains the same. So at x equal to 0 you have a force equal to Ra, and the magnitude of Ra is 20.82. So you have from here you have 20.82 going all the way up. So magnitude here is 20.82, and to the next point there is no change. So up until you reach this point here, there is no change. So you continue as a straight line here. Make sure that you draw this as a straight line. I have drawn it not like a straight line, but it is always a straight line because the force here and here are same. Now is the complex bit. You have a force varying based on this equation, which is a square law, and therefore you have to create a curve to show that variation from 20.82 here. Now you got to see that here I have added a plus sign, which is not correct because the force is acting opposite to RA, so that will be minus. So the force is varying from RA to RA minus 50. So 20.82 to a point where the net force is 50 minus 20.82 is minus 29.18. So you have a point somewhere here which is just below this point where the magnitude is 29.18 below the datum. So you will have a curve like this. I'll draw once again. You have a curve, not a straight line, a curve like this. It's a linear curve. There is no changes. But the thing to note here is that here the magnitude is RA minus 50, which is equal to 29 minus 29.18. And then, as you can see, between your between the third in the third section, which is between D and B, you do not have a variation in force, because that is, again, this is not plus, this is minus, and this also is minus. So that remains the same between those two sections. So you have the same force continuing here until you reach this point here, the end point. So this is a straight line, and at which point you reach the point B, where you have a reaction at B acting upward, which is 29.18 plus 29.18, and you have a negative 29.18 here. Therefore you can close your shear force diagram with that plus 29.18, and you have completed your diagram here. So that gives you the complete shear force diagram. Now just make sure this is a curve. This is a smooth curve. I can't draw this here because of the limitations of this software, but just make sure this is a smooth curve. It's just a curve like this, it's just a curve like this, and a smooth curve. So it's just because that variation is based on a square law that you have a curve there. Note that in case of a uniformly distributed load, if that was a uniformly distributed load, then you would have had a straight line, an inclined straight line there. It's not a straight line, a line from 20.82 to minus 29.18 here. It will be a straight line, but in this case, because it follows a square law, you will have a curve. Hope this explained the conditions and the situations very well. Please comment your opinions and doubts on the video, and once again, thank you for watching.